Okay, good morning. Hopefully your brains are starting to thaw out. We're all good? Okay. So let's talk a little bit about the assignments, and then we'll get back to lecture material. So hopefully, undergraduates, you submitted assignment 4, and you're on to assignment 5. So let's talk a little bit about assignment 5 for a moment. So assignment 5 is one of these assignments where, again, we're combining two Reddit assignments into one CS206 assignment. So there's 5A and 5B. 5A is going to be a little bit of refactoring, and 5A is refactoring, 5B is going to be random search. Who knows what refactoring means? Clean up, right. Basically, we're going to do a little bit of cleaning up here. So let's have a look at refactoring. If I can find it here. I had it here. Okay, so in the refactoring project, you're going to be modularizing your code a little bit. So you've now built all of the pieces to make your robot. You create your simulation, you send all the objects, you send all the joints, you send all the sensors, you send all the neurons, and finally you send all the synapses. So we're going to take all of the material that makes up the robot and compartmentalize it into a class called robot. So who has experience with object-oriented programming? Some people, maybe not everybody. Okay, so if you are not familiar with object-oriented programming, there's a link there. You might want to go and have a little bit of a look. Object-oriented programming, as the name implies, is creating objects in your code. So an object is a special kind of data structure where an object can have both variables and functions associated with it. A function that belongs to an object is called a method. You'll see that as you go along. You're going to define this class called object, and inside of the class called robot is going to be a constructor. So every time you create an instance of this class, whenever you create it, this special function called a constructor is called, and it's going to send all of the material that makes up that robot to the simulator. Okay, so usually we talk about classes and objects. So an object is a particular instance of a class, but we already have objects, which are the pieces that make up the robot. So I'm going to try and talk about classes and then a class instance, which is an object. So just try and keep our terminology straight. Okay, so by modularizing your code in this way, it should be relatively straightforward. To manipulate your code and extend it as we go. So for example, later in this assignment, you're going to be iterating 4 times through this loop, and every time through, create a simulator, create a class instance of robot, send that robot to the simulator, and wait for the simulator to finish. So you're going to send 4 robots, one after the other, using this function, or using this class. Okay. Just to sort of have a feel for where you're going, again, some of you have moved ahead with this assignment, but we're now going to have this class called robot, and inside of robot we have objects, joints, sensors, neurons, and synapses. As you move forward into 5B, random search, we're going to create a new class called individual, and as I mentioned, classes can contain both variables and methods. So individual is going to contain a class instance of robot. It's also going to contain another variable called fitness, and that's just going to store a single number, which is the quality of the behavior of your robot. Okay. From random search, we're going to go on to a hill climber, and then onward from there to a parallel hill climber and a genetic algorithm. So if you remember back a few weeks to our discussion about evolutionary algorithms always maintain a population of candidate solutions to your problem. Some of the individuals in that population survive, some die off, some produce offspring, and so on. So you can probably see where this is going. we're going to define eventually another class instance called population. And this particular class is going to contain a list, or actually a dictionary, of multiple individuals. Each one of those individuals has a robot associated with it and a fitness associated with it. So by the end of, actually all the way up to assignment 10, you're going to have a single instance of this, which is going to have a bunch of these, a bunch of robots and fitness, and so on. So this class hierarchy is what you're going to be building up over the next few assignments. Any questions about that? Okay, let's have a very quick look at the random search algorithms. So assignment 5B here. Not that different from what you've been doing so far. The main difference in 5B is at the end here, instead of creating a screenshot, you're going to be creating a video of your robot jumping around. And in this case, if you've got screen capture software, go ahead and capture the video directly from your screen. If you capture it with your phone, that's fine too. Again, we're not taking any points off if your video isn't perfectly beautiful, as long as we can see what we need to see in that video. Upload it to YouTube, which obviously gives you a YouTube URL. You submit the YouTube URL to Reddit. So now, like usual, you have a Reddit submission. Take the URL of the Reddit submission and post that back on Blackboard. Sound good? Okay, that's assignment 5. And if we go back to the schedule, the graduate students, you're working on assignments 9 and 10. So let's have a very quick look at 9 and 10. Okay, so assignment 9, you're going to be implementing a genetic hill climber. So for those of you that have got this far, at this point you have a parallel hill climber. And in a parallel hill climber, you have a population of individuals. Each one of those individuals is a parent, and it produces one and exactly one child. If child 1 is better than parent 1, it replaces it, and so on all the way down the line. One parent, one child. What's the difference between a parallel hill climber and a genetic algorithm? Both maintain a population of individuals.
Well, one's replicating sexual reproduction.
That's right. So there is sexual reproduction involved between parents. It's actually not in. I didn't actually put it in this one. It's still just mutation. There's another important difference between a parallel hill climber and a genetic algorithm. If you remember back to our lecture on evolutionary algorithms. Okay, you can go back and have a look. But the main difference here is in a parallel hill climber, every individual in the population produces exactly one offspring. In a genetic algorithm, individuals that have higher fitness produce more children than individuals that have lower fitness. So some of the individuals in your population who have very low fitness might not produce any offspring at all, and the better individuals in the population might produce 2 or 3 or 4 offspring per generation. Right? So we're starting to do a better job of approximating biological evolution, where again, individuals that are able to survive and find a mate and so on produce more children than those that die early or unable to find a mate. Okay, that's the main difference in the genetic algorithm. Genetic algorithms sometimes include sexual recombination. We haven't put that in there yet. We might put that in a little bit later. Okay. So for the graduate students at least, that's 9. And then moving on finally to 10. In 10, you're going to be changing your fitness function. So at the moment, you're selecting for robots that locomote as quickly into the screen as possible. Now you're going to change your fitness function to select for phototaxis, which, if you'll recall back to our discussion about Bratenberg vehicles, is what? I guess it kind of says it up there already somewhere. No? It's phototaxis.
Like reacting to light?
Reacting to light in which way?
Either running away from it or approaching it?
Exactly. So taxis just sort of means you're reacting to light somehow. So there's photophobia, running away, and photophilia, running towards. We're going to do photophilia. So we're going to be evolving a robot that will figure out how to move towards a light source that we place in its environment. And at the end of assignment 10, you should have a robot that's doing something like this. You can see the light source inwards towards the screen. And we've got a robot that's not walking perfectly well, but at least walk towards the light. Here it's turning to the right and moving towards the light source on its right. Now the robot starts moving forward, turns a little bit to the right, and slowly but surely turns and comes back towards the light source behind it. In this fourth and final environment, I don't know what it's doing. It's not doing the right thing, whatever that is. So phototax is an exceedingly challenging task to get your robot to do. So if you get a robot that walks towards 2 out of the 4 light placements, that's fine. 3 out of 4 is great. If you manage to get 4 out of 4, we'd love to hear from you. That's a tricky thing to do. So the big challenge in assignment 10 here is really just getting some evidence that your robot is starting to evolve to exhibit, well, photophilia in this case, moving towards the light. Okay. So in order to do that, we're going to introduce another class called ENDS, and as ENDS sounds like, it's a set of environments. So in this case, we've got 4 environments. So we're going to create another class called END, so just a single environment. And this particular class instance is going to contain all of the information we need to create the environment for our robot. So up till now, you're evaluating one robot in one environment. In the phototaxis task, you're going to take each individual in your population, and for each individual, you're going to evaluate it 4 times in these four environments. In each environment, we're going to get a fitness value. How close to the light source did this robot get to the light source here? How close did it get to the light source here? How close here? And how close here? So we're getting back 4 fitness values for each individual. What do you think we do with those 4 fitness values? What's that?
I say that calculate the average.
You just take the average, right? On average, how well does the robot do at approaching the light? So the robot that I just showed you did pretty well. It got 3 out of 4, right? So it was doing better than the other individuals in the population. So we're going to get a fitness value back from each of these 4 environments, and we're going to average them and set the fitness of the robot to its average ability in each of these 4 environments. So when we actually evaluate our robot, we need to send in ends. So this is going to be separate from population. So the top part of your code, you're going to define 2 class instances. One population and one set of environments. And then when you start up your genetic algorithm on your population, you're going to supply ends into each individual. Okay. So that will conclude assignment 10, and that will be all of the assignments we have for this course. So when you end assignment 10 here, you're going to have a genetic algorithm, which is evolving a population of robots, and it's evaluating it against multiple environments. Once you've finished assignment 10, you're going to formulate your own project, and you're going to be working on that throughout the rest of this course. Grad students will talk about projects when you finish assignment 9 and 10 next Tuesday, and for the undergraduates, we'll talk about it when we get there towards the end of March, beginning of April. Okay, any questions about the assignments? We're all good? Okay, so let's get back to lecture. So the timing has worked out pretty well here. So you've basically worked your way through it by assignment 5 here, all of the basic tools of the trade, right? We have our robot, we have our physical simulator, we've created the neurons and synapses that make up the artificial neural network for our robot, and we're evolving our robot using an evolutionary algorithm. Okay, so we're now going to finish our lecture on physical simulation. There's a few slides left, and then we'll move on to the next theme of the course, which is the history of evolutionary robotics. Okay, so just as a very quick reminder, we were going through some of the code from Open Dynamics Engine, which is the physics engine embedded within PyroSim. We looked at what ODE is doing for every time step of the simulation. We have this loop, and every time that it's looping through, after setting the physical and geometric properties for all our objects and connecting them together with joints, and determining what should happen when objects collide with one another. We then start up this loop where every pass through the loop, ODE is figuring out which objects have collided with which other ones and apply forces to those objects, pushing them apart. Add all the other forces to each object, so gravity is pulling objects down. If an object is touching another object, is there friction slowing that object? Is there torque acting on a joint? So is there rotational force that's causing an object to rotate relative to one another? ODE is summing up all the forces that act on each of the objects. And then at this line here, it updates the world. It computes the new positions and orientations of the objects based on their forces using the equation you saw in high school physics, force equals mass times acceleration. It's not that much more complicated than that. Okay, throws away all the contacts, and assuming that you have the graphics turned on, it will draw your scene and then rinse and repeat. Update the physics, draw, update the physics, draw, and around you go. So ODE will take care of the physics for you. What it will not take care of for you is the robotics side of things. So under the hood in PyroSim is some additional code that's been put in there to simulate sensors, motors, neurons, and synapses, which ODE doesn't have, but we can simulate them by exploiting the physics that ODE is doing for them. So we ended last time by looking at a few examples. So if we wanted to, for example, create a sensor for a robot, if we wanted to create touch sensors, we can do so by looking at all the objects that contain a touch sensor. And if that object is colliding with another object, we set that touch sensor, otherwise that sensor is not set. We talked a little bit about simulating a light sensor, which you just saw in the phototaxis example. So in the phototaxis example, there was that white light source off in the distance. It's emitting a light. In order to detect what the light level should be for a light sensor sitting on the robot, we take the distance between those two objects, and then we take 1 over 1 plus the Euclidean distance. And I apologize, I realize now that equation is incorrect. What's actually going on under the hood is 1 over d squared. So we compute the distance between the light sensor and the light source, and then we set the value of the light sensor to 1 over d squared. Why 1 over d squared? It is the inverse square law, right? So imagine you have a light source. If you're right close to that light source, you're bathed in a lot of light, right? The light intensity is very strong. But if you imagine the light emanating out from that point, it's getting more and more diffuse the further away you are, right? It's spreading out in a sphere around the point, and it falls off with the square of distance. So once you put a light sensor on your robot, it starts moving around, that light sensor will activate with 1 over d squared. Okay, you've started to see that there are other sensors in PyroSim. So there's a proprioceptive sensor that reports the angle of the joint. There's also a vestibular sensor in there, which is like your inner ear. So your inner ear will tell you how your head is oriented relative to gravity. You can put a vestibular sensor in the robot, and it will know how its body is oriented relative to gravity. You can try and figure out for yourself how, given what you now know about physics engines, how might you simulate those sensors? And if you're interested, you can dive down into the C side of the code and actually see how we simulate those sensors. Okay, but that's optional. Okay, so you get sort of a feel for how we simulate sensors. How about motors? Remember that if you just have a joint and there's no motor neuron attached to it, it just rotates passively, right? So your robot is basically like a rag doll. The joints will move as the robot sort of falls and settles to the ground. The minute you connect a motor neuron to a joint, that joint becomes motorized, meaning that at each time step of the simulation, the neuron is going to apply a force at that joint. How exactly does that work? Inside the code, if you connect a motor neuron to a joint, like for example this joint here, we set some parameters of the hinge joint. And one of them is the total amount of force that can be applied to that joint. That's something we set up front. Imagine for a moment that our motor neuron is outputting 60. Remember that motor neurons output a value between -1 and +1. And we then scale that to whatever the range is of the joint, which you can set. In the code at the moment, we're setting the range of the joints to rotate between -45 degrees and +45 degrees. So in this cartoon example here, let's imagine that we can really rotate between, -90 to +90. At this point in time, let's imagine that the motor neuron is outputting a desired angle of 60. We call an ODE function that gives us the current angle of the joint, and we then simply take the difference between the desired angle and the actual angle. And we then take that difference and we set at the hinge the velocity of the hinge. How much should it start accelerating, or what should its velocity be at the next time step? What if, in our example here, just for the moment, let's assume that the actual angle is 60. What happens at the next time step?
It would slow down.
Slow down, right? So desired angle is 60, actual angle is 60, difference is 0, so the velocity, the desired velocity at the next time step is 0. If the joint is at the angle that the motor neuron wants it to be at, don't apply any force. If something pulls that joint away from that desired angle, so for example, let's imagine in this case that at the first time step in this simulation, the angle is actually 0 degrees. Remember, at the first time step of a simulation, the moment you connect pairs of objects together, that joint angle by default is 0. So we have an actual angle of 0. The desired angle is 60 degrees. The error is 60. So you can see in our little cartoon here, the velocity is 60. So it's ODE is trying to apply a torque, this rotational force, that's going to make sure that at the next time step, the leg, in this case, the front leg of the robot, is rotating forward at 60 radians per second. So it's starting to rotate forward. Okay. The moment it starts to rotate forward, let's imagine at the next time step, the angle is now at 20 degrees, but we're still asking for a desired angle of 60. So we've got 60 minus 20 is 40. What happens at the next time step?
Keeps shifting.
It keeps shifting, but how does it keep shifting?
Slower.
Slower, right? So the desired velocity that we sent to ODE was 60. At the next time step, it's 40. Now at this point, it doesn't actually get all the way to the desired angle of 60, right? It's rotating a little bit closer. In this cartoon, it should probably not be 40. It should be something less than that. But let's imagine now the error is 20. So as the leg is rotating, what happens as we iterate forward in time in the simulation?
You approach the angle that you want.
Exactly, right? Assuming that the motor neuron continues to output a desired angle of 60, the leg will rotate forward until the inner angle reaches 60, and then it'll come to a stop.
How are we dealing with velocity and not just force here? Why aren't we doing force to counter gravity?
That's a good point. So we're letting, as always, we're letting ODE figure out what the forces are, right? We put an object 1 meter above the ground, and ODE figures out that the only force acting on that object is minus 9.8 meters per second, right? So in everything we're doing in the physics engine, we sort of do everything up to but not including telling it what the forces should be. In the case of our motorized joint here, we're supplying a desired velocity, and that velocity is the difference between actual and desired. ODE will figure out if that's the desired velocity at the next time step, how much torque should be applied to do so. The leg might actually already be in motion, in which case there's inertia, right? It doesn't have to apply a lot of force to make sure that it continues rotating forward. It depends on what the entire robot is doing. There's actually a complex mapping from this desired velocity to the torques to apply to make sure you reach that desired velocity at the next time step. Make sense? Okay, let's look at one more example here. So I've shown you sort of how we simulate sensors in ODE. I've showed you how we simulate motors, motorized joints in ODE. What about simulating a neural network? So we've got, again, our example here where we've got two touch sensors in the back and the front leg of the robot. And let's imagine that we create two sensor neurons, T1 and T2, and one motor neuron, M1 here. And let's assume at the beginning of this particular simulation, both legs are in contact with the ground. So they both fire. And in this cartoon example here, imagine we have two synapses that connect the two sensor neurons to the motor neuron, and it produces an output of 60. The motor receives a desired angle of 60, and as we just saw on the previous slide, the leg starts to accelerate forward. The moment the leg accelerates forward, the leg leaves the ground, which means T2 stops firing. So at the next time step, the input, the sensor neurons in our neural network are 1 and 0, right? The robot has moved, and the moment that it's moved, there's been a change in the sensors. And let's assume, continue to assume in this cartoon example here, that now, because the input is 1 and 0, the motor neuron outputs a desired angle of minus 90. Remember, the motor neurons range between -1 and +1. I'm just expanding it here over the actual range of the joint. What happens at the next time step? The joint received a desired angle of 60, so it started to rotate forward. The moment it did, at the next time step, it now receives a desired angle of minus 90. What happens at the next time step?
Because the velocity is determined by the difference of the desired angles, is it going to go really quickly this time?
Really, it's going to go more quickly now, right?
Shift back fast.
It's going to shift back, right? So it's a negative number, and remember that we're going to set everything up in the simulation so that flexion, meaning rotation in towards the body, are negative numbers, and extension are always positive numbers, which are rotating body parts away from the center of the body. Flexion, negative numbers, extension, positive numbers. Okay, so the leg starts rotating back inwards towards the ground. What happens the next time step? You've probably already seen your minimal robot with these two cylinders do exactly this. What happens the next time step?
Keeps moving towards itself.
The front leg will rotate down. What happens as it starts to rotate down and towards the main body?
Which will stop like at the body.
Will it stop at the body?
Or its desired angle.
So the desired angle is minus 90, right? So the leg is a little bit out in front here. At the next time step, because of the minus 90, it's going to start to rotate inward again. It's going to reverse direction and start coming back again. What's going to happen?
It's going to touch the ground again.
It's going to touch the ground, in which case this happens, which means it's going to do this, and this, and this, and this, and it'll start to scissor forward, right? You've probably already seen your robot doing exactly this, right? So, as I mentioned before, by connecting the sensors to the motors, we've closed this feedback loop between R, the robot, and E, the environment. The robot moves, and the moment it moves, its relationship with the environment changes. which causes its sensor values to change, which causes the way it moves to change, and iterating through this feedback loop is what we call behavior. Right? And we can modify what kind of behavior we get by changing the weights of, at least in this cartoon example, these two weights here. So just to shake the rust off of our intuition about neural networks, let's assume in this little cartoon neural network here, there's no thresholds, there's no tan H. All we have are the two synaptic weights. What are the two synaptic weights? In this example here, when both inputs are 1, we get a 60 at the output. And when the inputs are 1 and 0, the output is minus 90. What are the weights?
-90 and 150.
Right, so this makes it easy, right? We know that because this is 0, it's having no influence on this output neuron. So this value has to be this value times this value. So this weight has to be minus 90. And if this weight is minus 90, we have 1 times minus 90. So we've got minus 90 here, but we need to get to plus 60. So this weight has to be 150. Minus 90 plus 150 gives us 60. Okay, very simple neural network, very simple cartoon example here. But there's our robot, right? Even with this simple setup, we can get relatively sophisticated behavior like legged locomotion. Right? Okay, that concludes lecture 6. Any questions about physics engines? Again, all the reading for this lecture comes from the user manual. So for those of you that are interested in the nuts and bolts of how physics engines actually work, it's all there for you. Okay, so let's switch now and move ahead to the history of evolutionary robotics. As I mentioned, this is not like calculus, which has been around for several hundred years. Evolutionary robotics is a very young field, started in the early 1990s, and we're going to talk about the two first experiments in evolutionary robotics today. We're going to talk about the Italian approach and the English approach. The two experiments were carried out by Italian and English researchers. Just to make things a little bit more confusing, the Italian researchers were in Switzerland, but there you go. Okay, so this was one of the state-of-the-art robots back in 1996. This is the Kepler robot. It's kind of a nice robot, and versions of it are still used today. 55 millimeters in diameter, so a very, very small robot. What's the nice thing about having a small robot? Especially if we're going to try and evolve behaviors for this small physical robot.
Less to worry about?
Less to worry about in what sense?
The bigger the robot, the more sensors and motors it needs.
The bigger the robot, the more sensors, the stronger motors.
Small robot, small environment.
Small robot, small environment. So all the experiments we're going to see in a moment were all done on a tabletop, right? You don't need a football field or what have you. Okay. So, there you go, right? It could be carried out on a table. All right, nice thing about the Kepler robot, it was also somewhat plug and play, somewhat sort of modular. So at the lowest level, we had a robot with 2 wheels and a couple sensors on the front. Should start to sound pretty familiar. The Kepler robots were inspired by the Bradenburg vehicles, exactly, right? So you can plug on other extensions. For example, here's a gripper, and that gripper is grabbing a little sugar cube and lifting it. Kind of a nice tool for evolutionary robotics. You could also add on a simple linear vision module here. So this little linear visual module here had 64 photoreceptors, and each photoreceptor would cover a visual field of about 36 degrees. If there was an object, a vertical object in front of the robot, then the photoreceptors would respond with high values. And assuming that this object is relatively dark, the photoreceptors would give back a lower value. Right? Okay, so it's not a full camera, but again, we could start to get the basics of interesting sensation like vision and action like object manipulation. Okay, that's the Kepler robot. So back in the mid-90s, Floriano and his colleagues reported in the literature this first evolutionary robotics experiment, which was done with a physical robot. Why didn't they use a physics engine? Would have been much easier. There were no physics engines back then. The first one was sort of released on the market in 2000. So we got to do everything with physical robots. So kind of an ingenious setup here. They have their Kepler robot moving around on a tabletop, and that robot is tethered to the computer. And as you would imagine, there's not a lot of computation available on the robot. So they did all of the evolution on the computer, and the robot did the behaving. Not only that, but they also simulated the robot's neural network on the computer. So the brain of the robot was not even on the robot. It was all done on the computer. What the computer would do would be to send motor commands, take the values arriving at the motor neurons, send those to the two wheels. So in this cartoon, there's 8 here, but it should really just be two motor neurons controlling the two wheels. The robot moves, it gets a little bit of sensation back. It reports that sensation back to the computer. That gets fed into the input layer. The computer transforms the sensor values into motor values, and around you go. Okay, what exactly does the robot sense? So the robot had, in this experiment, a little positioning turret on top, and that turret would actually detect lasers being emitted from this little gantry up in the top here. So given the robot receiving this laser sensor information, the robot could determine its current position, x and y, so not x, y, and z, because we have a robot moving in 2 dimensions, and its current heading, alpha. So the robot could give back at least these 3 numbers, and away we go. Okay, so we've closed the loop between the robot and its environment, and we have a genetic algorithm here. So we have a bunch of individuals in a population. At the next generation, we have other individuals in the population, and so on and so forth. So we can run evolution and evolve our robot to do something. If you had this particular robot with this setup, what might you evolve it to do?
React to the light.
React to the light, we could do that. What else could we do? There's a little hint if you look at the cartoon here of the experimental setup.
Avoid obstacles.
Avoid obstacles. How would we do that?
Drive towards the white.
Okay, exactly, right? So we know it can see something, so it's going to have to try and avoid dark regions and go towards light regions. So here was the actual setup that they used. So we had X, Y, and alpha of the robot. So from the experimenter's point of view, we knew exactly where the robot was and its heading. But they made a change to the experiment, which is they did not take those 3 numbers and supply them to the input of the neural network. Instead, they had 8 proximity sensors, 6 on the front and 2 on the back. And those 8 values were supplied to the 8 sensor neurons that made up the neural network. Okay. Then they made this little maze or racetrack for their robot here, and they created a fitness function for their robot, which is circle through the maze as quickly as possible, don't hit the walls, and don't hit the walls. Okay. We're also going to assume that the wheels can go backwards and forwards, so the values arriving at the motor neurons could be positive and negative. Negative numbers rotate the wheels back, positive forward. And the robot's 8 proximity sensors return 0 if they can't see an obstacle, and the closer the obstacle is, the closer to 1 that proximity sensor fires. Okay, given those sensors and those motors, and that's what we want the robot to do, what's the fitness function? You're going to have to use the 8 numbers, the 8 sensor values, to compute the fitness function. You have the 8 sensor values, and you also have the 2 values arriving at the motors. So you know how fast the wheels are spinning. How would you construct a fitness function for this robot that selects for robots that circle through the maze as quickly as possible and don't hit the walls?
you would want to minimize the proximity sensors and maximize the wheels.
You want to minimize, exactly, you want to minimize obstacles. So we minimize the proximity sensors, right? So they want them to fire as little as possible. And we want to maximize the wheels. What will that give us, assuming that a robot evolves with that?
Stays away from the walls and still goes quickly.
Okay. Let's have a look at how the researchers did it. It's very close to what they actually did. All right, so phi is going to represent our fitness function. We're going to construct our fitness function so that it always ranges between 0 and 1. 0 is the worst possible thing that the robot can do, and 1, which may not actually be physically reachable by the robot, is going to be a robot that's zooming around and around the racetrack. Okay, we're going to construct phi out of I1 through I8, the value of the proximity sensor, so I for input, and VL and VR, which is the speed of the left and right wheel. Okay, this fitness function actually has 3 terms. You can see that all 3 of these terms are multiplied together. We're going to see a lot of fitness functions throughout the rest of this course. Pay attention because you might want to use some of these tricks in your own fitness function when you get to your final project. There isn't just one thing that we want our robot to do here, right? We don't want it just to go quickly, and we don't want it to just avoid walls. If it just avoided walls, what would be the best thing to do? Stand still, right? And if the only thing you had to do was maximize your wheels, what would you do? You'd smash into the wall as fast as you possibly could, right? So we actually have these 2 sort of competing terms, right? Evolution is lazy. We would like to do one thing or the other. So we're going to multiply these terms together, which select for these different components of the behavior we want. For those of you that have reached the quadruped assignment, you might see that the quadruped sometimes actually does run forward very quickly, and sometimes it flips over and starts thrashing around on its back. Right? You could modify the fitness function for the quadruped that selects for moving as quickly as possible, multiplied by a penalty for flipping over. Okay, so let's have a look at this. So uppercase V is the absolute value of the left motor plus the absolute velocity of the left motor plus the absolute of the velocity of the right motor. Why absolute? It's not quite what you had in mind, right? It isn't just a maximization of VL and VR. Why the absolute?
Well, is that because the negative values still count as a maximization?
They do in this case, right? By taking the absolute. But why did they do that? Why are the investigators considering high magnitude negative numbers fine?
Because it'll still be going quickly, just backwards.
Exactly, right? Remember that our robot has 2 proximity sensors on the back, so they didn't want to specify go forward, just go. So given this fitness function, they're giving evolution the freedom to discover a controller that gets the robot to race forward around the track or maybe backwards around the track. Right? If they had just maximized VL and VR, they'd say we only want forward travel. Right? Okay, what about this delta V term here? Why is that in there? Let's talk about what delta V does first, and then what 1 minus the square root of delta V does.
Wouldn't that give its which direction it's turning in?
Which direction it's turning in, right? So when delta V is equal to 0, what does that mean about the robot?
It's going straight.
And when delta V is high, or far from, yeah, exactly, when it's high, it's turning. Which direction is it turning in? Either one, right? So if the robot is standing in place and turning clockwise or counterclockwise, delta V is high. The delta, or the difference between the velocities of the 2 wheels, is high. It's turning. If it's staying still, or moving quickly forward, or moving quickly backward, delta V is 0. Okay, so we know what delta V is. It's how much turning the robot is doing. and then they take 1 minus the square root of delta V. Why? We're trying to maximize phi, remember, and we're putting this term in there.
Maybe to slow down the turning so it's not.
To slow down the turning, right? So 1 minus this thing means it's a penalty term. The more delta V you exhibit, the lower your fitness. This is a reward term, right? The higher V, the greater V, the more fitness you get. This is a penalty term because the higher the V, the lower your fitness. So they're rewarding robots that exhibit V, that go fast, and they're penalizing robots that turn. Why penalize robots that turn?
You could end up just with a robot that just spins in place going really fast, but not actually moving anywhere.
Absolutely. So imagine that I'm a robot and my VL is 0.5 and my VR is minus 0.5. Right? But I'm taking the absolute, so awesome, I got a good value for V, but that's not what the investigators had in mind. So they want to leave the flexibility for the robot to go forward and go back, but they don't want it exploiting this to turn on the spot. If you turn on the spot, it's going to be easier to stay away from objects than if you start moving. Yeah? I'll bet you that the investigators started this experiment with just V and just this term, which penalizes for getting near the obstacles, and they expected to get fast forward travel through the maze or fast backwards through the maze, and instead they got an instance of perverse instantiation. We're going to see this many times in evolutionary robotics. So perverse instantiation means that a robot probably evolved that instantiated what they asked for. They probably got a robot that had very high V, but it instantiated it in a perverted way. So not what the investigators had in mind. So I'll bet you they then added in this penalty term for turning. Okay. What about I, right? The maximum firing proximity sensor. Why the maximum? So remember we have these proximity sensors, which you can think of like these vertical bars here, right? The robot has 8 proximity sensors, and they're all reporting how far they are from an obstacle, if at all. Why take the maximum?
That's where the wall is closest.
That's where the wall is closest, right? So if at a point in time, if the robot is approaching the edge of an object and only one of the 8 proximity sensors is really firing, saying, look, we're about to hit something, compared to all 8 of them firing, saying we're close to the surface of a wall, who cares? Those are both equally dangerous situations, right? So forget about the average, just take the maximum, right? Try and minimize the maximum firing of your proximity sensors. Okay, so we multiply all those 3 things together. So we're selecting for V, and we're penalizing for delta V, and we're penalizing for I. What do we get? You get something like this down here. So this is a visualization. Again, remember this is mid-90s, so please apologize the computer graphics here. We're visualizing one of the evolved behaviors, and you can see that, yes, absolutely, the robot is moving through the maze. What do you think each of these little lines means? Can't see the actual robot here, right? We just see its trajectory. What are these little lines?
Wheel axle.
The wheel axle, right? So you can tell from this line which direction the robot is looking in, right? We can see that when it gets here, it actually slows down a little bit. Looks like it's kind of jittering, turning on the spot, and then accelerating. So you can actually see, thanks to these wheel axles, not just the direction of travel, but also the speed of travel. Okay. You're going to start to produce a lot of these kinds of plots once you get into your final project. So here we can see their evolutionary algorithm running, the number of generations. They're plotting, it's hard to see in this. This is the fitness of the best robot in the population, and this is the average fitness of all the robots in the population. So they ran this for about 100 generations. It took them 40 minutes to try out each neural network on the physical robot, one after the other, in this little tabletop robot. So it took them actually 66 hours in total to carry out this experiment. There were probably also lots of breaks to fix the robot and fix the laser emitter and all sorts of things. So when you start up your evolutionary algorithm, you can go get a coffee and come back and see what happens. You're lucky, right? Good thing physics engines were invented. Okay. You did not want to be a grad student in Floriano's lab back in this period. There were a lot of very late nights.
How would it know when the generation is complete? Is it just one lap, or does it just run for 40 minutes?
Okay.
And reset it?
Good question. So how does it know how long a generation is? Remember that a single generation corresponds to evaluating each individual in the population, right? So it doesn't say how many individuals there are in the population in this experiment. It's probably in the textbook. Let's imagine, for the sake of argument, that there are 40 individuals in the population, and it took 1 minute to evaluate each individual. So we take individual 1, we take the neural network in that individual, drop it into the physical robot, and let it go for, let's say, 30 seconds. I'm not sure how long it actually was. Let the robot run for 30 seconds. The desktop computer gets the fitness back and computes the fitness. That takes another 30 seconds or so. While the computer is computing the fitness function, the grad student reaches in, pulls the physical robot back to the starting position of the maze. The minute ends, and we now have the fitness of individual 1. We now have 39 more individuals to evaluate. Take the next neural network, drop it into the robot. Takes another minute. So 1 generation in this example takes 40 minutes. Make sense? Okay, so as we move forward, we're going to talk about generations, evaluations, environments. It's good to keep all this terminology straight. When we talk about a generation, that's short form for evaluating the fitness of every individual in the population. Okay, here's another fitness plot. So again, we have evolutionary time down here. This is actually plotting the same information as this, the fitness of the best robot in the population. But they've broken the fitness value into those 3 components, which were V, the total amount of wheel spinning, 1 minus the square root of delta V, the total amount of turning. But remember, it's 1 minus, so it's actually the amount of lack of turning. Kind of hard to wrap your mind around. And 1 minus I, which is the amount, 1 minus the amount of sensory stimulation, how close it is to an object. And we can see for the best robot in the population how those 3 components of fitness changed over time. Tell me about that. What happened in this best robot, or this series of best robots, whatever the best robot was in the population at every given generation? How did V and 1 minus I and 1 minus the square root of delta V change over evolutionary time here, from generation to generation?
Well, it's kind of interesting that the lack in firing, I guess, proximity firing, started really high and then it started to go lower. It's like, okay, it's okay if we get these little bits of firing.
That's it, right? So if we look at the dotted line here, this is, that's the, we're looking at the dashed line here, which is the total amount of sensory stimulation. It was jumping around quite a bit, but it actually stayed more or less constant over evolutionary time. So however close it was to the walls, the best robot always maintained about that distance. And that distance was, maybe about this far. Remember, this robot has these 6 proximity sensors arranged on the front. The closest one was probably always, in this case, this one. Maybe in this case it was this one. So it's always maintaining about the same distance from the wall, more or less, over evolutionary time. What else can you tell me about this sequence of best robots in the population over evolutionary time?
They were spinning faster and faster.
They were spinning faster and faster, right? So we can see that slowly over time, V is going up, right? So it doesn't necessarily mean that it was going faster. It was going forward faster or going backwards faster. Just the wheels were spinning, right? So in order to know whether it was actually getting faster, we need to also look at the dotted line here. And again, we can see that the dotted line is jumping around and then more or less kind of settles down through this period here while V is going up. So if the dotted line is telling us that this term is staying relatively constant, but this term is increasing, what does that mean during that period?
It is getting faster.
It is getting faster, right? So what are these robots doing? They're basically going very, very slowly, right? They're kind of sitting there, twitching a little bit, and then as the hours start to pass in this experiment and the days start to pass, slowly the robot starts to speed up and get a little bit more ambitious until at the end of 2.77 days, it's racing around the maze. Is it racing around forward or back? Can't tell, right? Not quite clear. Intuitively, we would kind of expect it's going forward, right? It would be easy, if you were in the maze, it would be easier for you to run around through the maze forward, right? Remember several weeks ago we talked about how thinking about thinking is misleading, right? It would be more comfortable for you if you were trying to maximize this fitness function to run forward through the maze rather than run backwards. But maybe not for the robot, right? Who knows? Okay, I just threw this one in. This is kind of an interesting plot. They tried to plot this in 3 dimensions here. So again, it's the same fitness curve where each point here corresponds to the best robot in the population. And we have the 3 fitness terms, V, 1 minus I, 1 minus the square root of delta V. And they're trying to show a trajectory of which of these terms in the fitness function evolution tackled first. Did it improve component 1, then 2, then 3, or did it improve all 3 together? I don't know if this is quite a successful way of doing it, but again, you might try something like this when you're evolving your robot and trying to understand how it's improving over evolutionary time. Okay. Let's have a look at a few examples here. So one thing they tried is to actually take a Bratenberg vehicle and build it right into the robot. So they set aside the evolved synaptic weights. They took their robot and they set all of the weights manually to simulate a Bratenberg vehicle. So you remember when we talked about synapses, we can actually have excitatory synapses and inhibitory synapses. And if you look carefully here, you'll see that the cross connections, so sensors on the left that connect to motor neurons on the right, are inhibitory. And ones that are on the same side have an arrow, meaning that they are excitatory. They also made the inner ones here a little bit stronger than the outer ones, but that doesn't matter too much. So this robot is bilaterally symmetric, meaning all of the weights on the left are the same as all the weights on the right, which is what Bratenberg said we should do. But it turns out the devil's in the details, right? If you have a bilaterally symmetric robot and it happens to drive right into the corner, what happens? It gets stuck, but why does it get stuck?
Because it's not turning, but it's going fast forward and backwards.
Right, so it's going in, it's probably not going in at a perfect angle. It's maybe a little bit closer to the right-hand wall or its left-hand wall, so it turns a little bit away from the left-hand wall, right? This is the coward, if you remember from the Bratenberg vehicle series. So it turns a little bit away from the wall that it's closest to, which means it's now closer to another wall, so it moves with the same amount of velocity, because it's bilaterally symmetric away from that wall. Now it's closer to the other. Right? So the evolved robot, when they had a look, they took the best evolved robot and put it at exactly the same initial condition as this guy, and it didn't get stuck. Why not? Who knows? Well, we know one thing for sure about this evolved robot. What is it?
Fitness function?
Not just the fitness. We know what the fitness function was. We know that the Bratenberg vehicle gets stuck in the corner, and our best evolved robot, when we put it in the same position, does not get stuck in the corner. Therefore, what do we know about this evolved robot?
It's willing to sacrifice the the whatever the 1 minus I for velocity.
Well, it's not willing to sacrifice 1 minus I. You can see what the evolved robot does
Or
is
the
it does a
1
quick U-turn and gets the heck out of
The
there.
1 minus delta V.
Okay.
When I sacrifice that for total velocity.
So we know about the fitness components. Tell me about the synaptic weights. Remember that evolution has set all of these synaptic weights. Again, we can't really know if we go and look at the individual weights what this thing actually is. But why do they compare this against the Bradenberg vehicle?
Well, it seems like it just arbitrarily chose that it prefers to turn left.
It prefers to turn left, right? It definitely has a bias. In this case, it actually is, that it tends to turn left more often than right. Again, what does that tell you about the synaptic weights?
They're not symmetric.
They're not symmetric, right? So we can take this evolved individual and point it right into a corner, which would stymie the Bradenberg vehicle. But the evolved robot, evolution figured out it's not a good idea to be symmetric in this case. It's always good to have a little bit of asymmetry, so you'll always be able to get out of tight corners. Okay? Again, something that in retrospect seems obvious to us, but a human engineer might not immediately do, right? A human engineer might prefer something that's a little bit symmetric, but you actually introduce a problem for the robot, right? So evolution often comes up with these kind of non-intuitive solutions. The body of the robot is bilaterally symmetric. All the sensors and motors and wheels are the same on one side or the other, but evolution has given this robot's brain an asymmetry to help it with this situation. There's another interesting quirk of this evolved robot, which is it only drives at 48 millimeters per second, but the top speed is 80 millimeters per second. Why did it top out at 48 millimeters per second? We can see that V climbed to 48 millimeters per second and then stayed there. But we're selecting for fast robots.
Maybe because this way it'll have a greater average velocity opposed to when it has to like speed up and stop and turn.
Why does it have to stop and turn?
Because it's going too fast.
Okay, this robot actually can go at 80 millimeters per second and get through this maze. It can turn while it's at 80 millimeters per second. So there's a good guess. It's not actually about the turning. No?
Does it have to do with the amount of time it takes for the sensors to emit a input and output?
It takes exactly a certain amount of time for the sensors to register what they see. If the robot is traveling too fast, if it's traveling at 80 millimeters per second, at the next time step, it's either hit the wall or it's way, way, way too close. So the thing that's slowing down this robot is not the speed of the motors, it's the speed of the sensors, right? If the refresh rate of your eyes was relatively slow, you'd probably move relatively slow as well, right? But again, it's not immediately obvious. If you ran this and you didn't know about the details of the sensors and you didn't take a moment to think about it, you might think there's a bug in your evolutionary algorithm, or maybe you need to run it for 27 days rather than 2.7 days, right? So evolution will often find these non-intuitive solutions that we might miss. Thinking about thinking is misleading. Okay. Any other questions about the Kepra before we move on? Okay, we've got 10 minutes left, so let's see how far into the English approach we can go. So while Professor Floriano over in Switzerland was working with the Kepra robot, a group at the University of Sussex was creating this very interesting robot here called the gantry robot. As you can probably figure out from this cartoon, they were also trying to figure out how to evolve robots using a table. And one of the things that's really difficult about evolving physical robots is at the end of every evaluation, you have to go in and grab the robot and bring it back to its starting position. The gantry robot was designed to automate this entire process. So when they were evolving the gantry robot, there was no grad student reaching in every 40 seconds and resetting the physical robot. It was all automated. How did they manage to do this? Well, as you can see, they had a table with an empty hole in the middle of it. And they then dangled down through the table what you can think of as an inverted periscope. You know the periscope on submarines that reach up and look like this? This is one that's reaching down. This periscope here has a camera that's now pointing downwards. It's a fixed camera that's pointing down towards the ground. there's a little dental mirror that's sitting on a rotational motor. So when that motor spins, this diagonally angled dental mirror starts to rotate. Why the heck would you ever build a robot like this? What does that allow the robot to do? See all around it, right? It's seeing from upside down, but again, the robot doesn't care. You might if we dangled you upside down through the table, right? But thinking about thinking is misleading. This isn't uncomfortable for the robot. Okay, so we know a little bit about this robot sensor already. It can sort of see around itself. This here is a little bump sensor. So whenever, if it comes into contact with something, this little disc will rotate because it bumped something, and it will activate some of the touch sensors in this little mount here. So our robot has touch sensors and a little bit of vision as well. Okay, that's the sensors. Let's talk about the motors. This robot has 3 motors. The first one wheels this X trolley horizontally along the table. And sitting on top of this X trolley is a smaller Y trolley that can drive itself back and forth along the X trolley. Again, seems like sort of a Rube Goldberg machine here. Why would you build such a crazy thing? What does that allow our inverted periscope robot to do?
Move in the XY plane.
It can move in the XY plane, right? So it can move anywhere. It can move the periscope anywhere underneath the table. They can place objects and make interesting scenes for the robot to try and navigate. Okay, so we've got back and forth on the X trolley, back and forth on the wall Y trolley, and then this tilted mirror that can be rotated. 3 motors and some vision and a little bit of touch. So let's see this in a little more detail. So I mentioned touch already. We've got this little circle here, a bump sensor. So we're going to simulate 4 touch sensors. Was this little circle bumped from the front right, back left, or front left? So our robot, in essence, has 4 virtual touch sensors arranged around it. And vision is a little bit more complicated. They have a CCD camera in here. So again, this is the mid-90s. It didn't have very high resolution. And they weren't going to take the entire pixel array from the camera and feed that into 200 times 200, which would give us 40,000 input neurons. This isn't going to work. So they gave Evolution the ability to downsample the visual input. So they could take again, I can't remember, it's probably not 200 by 200, but something like that. They took those 40,000 raw pixel values and allowed Evolution to boil those down to 3 numbers. And here's how Evolution does it. We have our CCD raw image that point at northwest, east, and south. They rotate the image a little bit. So this the mirror is actually spinning all the time. They get a 360-degree view all the way around from top to bottom and back again. And then Evolution spits out 3 triplets, so 9 numbers in total. The first triplet dictates the X and Y position of this circle, and the third number, R, dictates the radius of this circle. The second triplet dictates the X, Y, and R of this circle, and the third triplet dictates the X and Y and R of the third circle. So far, everything we've seen, we have an evolutionary algorithm that's modifying synaptic weights, right? If you have 1 touch sensor and 8 motors, we have 8 synapses, so we have 8 numbers that we're going to try and evolve. Now we have 9 numbers that aren't dictating synaptic weights. They're dictating what are called fovea, and you have these in your eyes as well. A fovea is the part of your visual field, that you can focus on. So the Evolution is in essence painting these 3 fovea onto the raw video feed. And at every time step of the evaluation of this robot, The computer will take the average grayscale of all the pixels in those 3 circles, and then downsample that to an integer between 0 and 15. So, for example, this circle here is going to have a value of 0. There's no gray at all. There's no white at all in this circle. This white circle here will probably report a value of 15. Right? There's a lot of white in this circle. So our robot can see sort of black and white, and only in these 3 places in its visual field that it's been evolved to look at. How many sensors does this robot have? So we're now going to build the neural network for this robot. We need to create a number of sensor neurons and a number of motor neurons. How many sensor neurons are there? Not 3.
7.
7, right? So we've got our 4 touch sensors plus our 3 vision sensors. So V1, V0, V1, V2, T0, T1, T2, T3, right? We've got a total of 7 sensors. These sensors happen to be reporting integer values. Doesn't really matter from the point of view of the neural network. So far, so good? Okay. Okay, and then those seven sensor neurons are connecting to just two motor neurons. What do those 2 motor neurons do? They control the 2 trolleys, right? The 3rd motor just spins the dental mirror continuously all the time. Yeah? So kind of an odd robot, right? What could we then do with such a robot? Well, they then evolved this robot to do something. They're going to evolve the neural network for this robot, the 7 sensors connecting to the 2 motor neurons, plus those 9 numbers that influence how the robot sees the world. And they're going to evolve this robot in an incremental fashion. So you'll notice that it says incremental evolution here, meaning that over evolutionary time, they're going to change the fitness function. They're going to select for different behavior as evolution proceeds. And as you can imagine, they're going to make that fitness function incrementally more difficult. Okay. So we're back to Phi1 here. So the first fitness function. What they did is they took they took one neural network plus those 9 numbers, downloaded it onto the physical gantry robot, and they evaluated that gantry robot 4 times. Remember our discussion at the beginning of this morning about phototaxis. They want to see the average behavior of this one robot in 4 different environments. The environment was actually the same. They just put a piece of black Bristol board at the back, so there's a big black patch back there. And they then moved the gantry robot to 4 initial starting positions. And the robot had to move towards the black Bristol board. How would you define Phi1? Given the sensors that this robot has. Remember, we're usually creating the fitness function from the actual sensor values generated by the robot. At every time step, the gantry robot generates 7 numbers, the 3 visual sensor values and the 4 touch sensor values. How would you define phi to select for robots that always move towards the back of the table, towards the black patch, regardless of where they are?
Well, probably 15 minus the minimum of the vision sensors, so it can move towards the dark patches.
15 minus the darkness of the patches, right? So if one of the patches is 0, that's pretty good. That means you're probably pretty close to the black Bristol board. 15 minus 0 would be pretty good. Okay, we're out of time. So as homework, think about what sort of fitness functions you might create for the gantry robot. You have a quiz due tonight, and undergrads, you're working on assignment 5. Grads, you're working on 9 and 10, and we'll see you on Thursday. Thank you.